Welcome to Module 3. This module covers protocols and ports. These are the two concepts that explain how devices on a network actually communicate. Not just that they can communicate, but how they agree on what to say, how to say it, and what to do when something goes wrong. By the end of this module, you'll be able to read a firewall rule and understand exactly what it's permitting or blocking. And you'll recognize the industrial protocol ports that appear in security discussions and vulnerability advisories. Before we get into specific protocols, we need to establish what a protocol actually is. This is one of those foundational concepts that, once you have it, makes everything else in networking easier to understand. A protocol is an agreed upon set of rules that governs how two parties communicate. Both sides of a conversation must follow the same protocol for the exchange to work. If one side breaks the rules, communication fails. Think about radio communication on a job site. There's an agreed upon format for how you call someone, how you identify yourself, how you confirm receipt. Dispatch says, Unit 4, respond to East Gate. Unit 4 says, copy and route. Both sides know the format. If one operator starts using different terminology or skips the confirmation, things break down quickly. You could say the same thing about instrument loop wiring. You use 420 milliamp because every device on that loop agrees on what that signal means. A device that decided to use 0 to 10 volts instead would fail to communicate even if it was physically connected. Networks work exactly the same way. A protocol defines the format and sequence of every exchange. Both sides must implement the same protocol or no data moves. A protocol specifies exactly how a connection is established and closed, how the data is formatted and packaged, how errors are detected and handled, and the order in which messages are sent. Nothing is left to chance or interpretation. When your SCADA server pulls a PLC using Modbus TCP, the server sends a specific byte sequence asking for specific register values, and the PLC responds with a specific byte sequence containing those values. The structure of both messages, down to the position of each byte, is defined by the Modbus protocol specification. If either device sends anything outside that specification, the other side rejects it or ignores it. This precision is what makes networking reliable. It's also why protocol documentation matters for security. When you know exactly what a valid Modbus request looks like, you know that anything that doesn't fit that structure is worth examining. Different protocols exist for different jobs, and they were designed at different times with different goals in mind. Web browsing uses HTTP and HTTPS, Hypertext Transfer Protocol. Remote access uses SSH, Telnet, and RDP. File transfer uses FTP and SFTP. Incidentally, a lot of these P's stand for protocol. Email uses SMTP, IMAP, and POP3. Industrial communication uses Modbus, DNP3, Ethernet over IP, Profinet, and others. Each protocol was designed with a specific purpose in mind. That design history matters enormously for security. Web protocols like HTTPS were updated over the decades specifically to include encryption and authentication. Industrial protocols like Modbus were designed in the late 1970s for serial connections between devices on a factory floor where physical access was controlled. Security was not a requirement because the network wasn't connected to anything outside the facility. When those same industrial protocols moved from serial cables to Ethernet and from isolated floors to connected networks, the protocols didn't change. The security assumptions they were built on, that the network is trusted, that devices on it are authorized, that nobody is watching the traffic, those assumptions no longer hold. That gap is the foundation of most OT security risk, and we'll continue to return to it throughout this module and this course. You'll hear networking people talk about protocol stacks or layers. This refers to the way protocols work together at different levels. A useful way to think about it: When your SCADA server sends a poll to a PLC, the Modbus protocol defines what question is being asked. The TCP protocol defines how that question gets reliably delivered. The IP protocol defines how the packet gets routed to the right device. The Ethernet protocol defines how the data moves across the physical cable. Each layer handles one job and hands the result to the next. We'll cover this layered structure in the next video, which looks at the TCP/IP model. Understanding the layers will help you reason about where different problems occur and where different security controls need to be placed. We'll see you in the next lecture.